Okay, so next we're going to talk about defining an order relation on the set of natural numbers. So here's the definition. For every m and n natural number, we define m to be smaller than n, and is denoted by this if there exists a q, a natural number q, in n, such that n is equal m plus q. Similarly, we define m bigger than n, all right, if there exists a p and n such that m is equal n plus. Also, we define as usual that m less than or equal n. So the meaning of this is either m equal to n or m is less than n. Sometimes we read this one as m strictly less than, the same thing as that. And also we define that m is bigger than or equal to m, and to be again either m equal n or m is strictly less than n. All right. I want to just state one theorem that's related to this. There are many others that, of course, connect the binary operations or the addition and the multiplication that you defined in n, how they behave with respect to these two relations, the less than, greater than, or less than or equal, greater than or equal. But I don't want to mention any one of these. So we're going to rely on our experience of all these different types of relations. That when you add two inequalities together, if you multiply and so on, what the inequality is basically the result. So the next theorem is this. And this is, we refer to this as tri-octony, a property. And it says that for any m, n, in n, one and only one and only one of the following relations is it true, or sometimes or hold. First one, m is equal to n, or 2, m is smaller than n, or 3, m is bigger than n. So given any pair of natural numbers, either they are equal to each other, or 1, denoted by the m is smaller than that, or the m is bigger than that. Okay? And this is a theorem. Right? It's not the fact it's a theorem which can actually be proven, but we don't want to go over the proof of this. The next objective is, as you know, the induction axiom is a very important axiom. We used it to prove variety of properties of addition and multiplication. We would like to look at two other properties or two other statements that are equivalent actually to the induction axiom. And by being logically equivalent means any one of these three, there are going to be three of them. So the first one is the induction axiom, and then there are two others. When we say these are logically equivalent means I can use any one of these to replace the induction axiom. Okay, and we can actually put it as part of the piano's axiom. But piano is actually stated the axiom using what we call induction axiom. And these are the will ordering principle and induction axiom, which we have it among the axioms for piano's axiom is called the first principle of mathematical induction. And there is another one which we call the second principle of mathematical induction, or sometimes called the strong principle of mathematical induction. And then the first one, we call it the weak principle of mathematical induction. We're going to show that all of these three are equivalent to each other. So let me state them, all right? So let me start with the will ordering principle. Will ordering principle. And we're going to actually denote this or abbreviate this is by WOP, will ordering principle. And this states F, basically I want to say F or let. Or let me actually just say like this. Every non-empty set of natural numbers means S, or in other words, you're saying that S is a subset of N. So every subset of natural number S has a smallest or least element in S. Okay, just to put it and to abbreviate this is equivalent to saying that for every S subset of N, where S is not empty, implies there exists a little s in S, such that S is less than or equal to X for every X in S. All right? So we call this is the will ordering principle. Then, for completeness, let me put what we call the first principle of math induction. Actually, this is nothing but the axiom of induction. And later on, we can actually restate it in a slightly different way. All right? And this one is saying that if K is a set of natural numbers not all of it, just a subset maybe, in n, natural number, such that 1, the numeral 1 is in K, 2, if K is in K for an arbitrary but fixed K, then K plus 1, which is the successor of K, because we know the successor of K is now K plus 1, is in K. So if these two conditions are satisfied by a set of natural number, then the conclusion of this, then K is equal to n. We're going to think of this again as a theorem now. All right? Then the third statement is we call it the second principle of math induction. So let me put it in here. This is, we call it second, or other name for it is strong. And for the first one, also we call it sometimes the weak principle of math induction. So in this case, it's very similar. The statement is if K is a set of natural numbers such that 1 is in K, the second statement in here, or second condition, is require that if 1, 2, 3, and so on, up to K is in K, again, for some fixed but arbitrary K, then the K plus 1 is in K. So if these two conditions are satisfied by a subset of natural numbers, then this subset of natural numbers is all the natural numbers. All right? So our next objective is to show that these three statements, three principles, the will-ordering principle, the first principle of mathematical induction, and the second principle of mathematical induction are logically equivalent. All right? But before we show that, I need a lemma that sounds, of course, is trivial, or something that we take for granted. But if we want to develop, again, the natural numbers using the axioms, we cannot assume anything except that something that we either have proved or stated in the axioms. All right? So this statement is the following. So we need this lemma. And the lemma states that 1 is the least natural number. Or when we state it in terms of integers, because from here on we're going to be allowing integers to come in, 1 is the least positive integer. Another way to state this means for every n in n, we have 1 is smaller than or equal to n. And we're going to do the proof of this using both the will-ordering principle and the induction principle, because we're going to prove the equivalence of the two principles of induction together with the will-ordering principle, and both of these uses this lemma. So we're going to prove this in assuming, either the will-ordering principle actually holds or the principle of mathematical induction holds. So let's do the proof based on the induction axiom. Okay, so the first proof is based on assuming induction axiom, or first principle of induction. I make a difference with do this, we call it first principle of induction. Okay, so we're going to assume this is the one which is true. And the proof goes like this. We're going to define a set of natural numbers, okay, to be n in n, such that 1 is less than or equal to n. Then I'm going to show that basically k is going to be all the natural numbers. Okay, so which means that all the natural numbers is going to be bigger than or equal to 1. Fifth, by the definition of k, 1 is in k, simply because since 1 is less than or equal to 1. Okay, so this holds. Because for an element in k, which is a natural number to be in k, it must satisfy this property. Well, 1 satisfies this inequality. All right, now next, let's assume that k is in k. And I want to assume k plus 1, or prove that k plus 1 is in k. All right, so this by definition of k, this means that k is bigger than or equal to 1. And this in itself implies that k plus 1, definitely this is going to be strictly bigger than k, because remember the way we define an inequality or the ordering, okay? So we say that either are greater than each other if there exists a natural number such that when you add, you come up with, which is k plus 1. So this is bigger than k. All right? And this one itself is bigger than or equal to 1. And by the transitive property, which makes the k plus 1 actually is strictly greater than 1. So which makes k plus 1 is in k. Because it does satisfy the defining condition of the set k. And now by the first principle of induction, or the induction axiom, by induction axiom, or again, it is written as a first principle, implies k is equal to n. And if you look at what k, how this is defined, as those natural numbers, they are bigger than or equal to 1, so it means that this statement is true for every natural number. Okay, we're going to do another proof, proof 2. This is based in assuming the will ordering principle holds. Okay, so we're going to assume the will ordering principle. Because we haven't shown that these are equivalent to each other yet. And I want to be using this lemma to achieve that proof. So I cannot use it, okay, if I'm proving that the will ordering principle implies, okay, the first principle of induction. I cannot use this because I'm using that, assuming that the principle is true. So that's why we need to prove it. So we're going to based on assuming will ordering principle holds is true. So what we're going to say, let's assume that, assume the contrary. So we're going to assume that there is let me say this by contradiction. By contradiction. Remember, this is what we want to show. 1 is the least natural number, which is equivalent to this. So we're going to assume that there is a natural number. So we can assume that there is a natural number A such that A is smaller than 1, which is the negation of every n is bigger than or equal to this, the negation of that. There is at least one natural number is actually smaller than 1. And we know this is because this is a natural number, this is going to be bigger than 0. Now we need to define a set S to consist of those numbers. This is equal the numbers or the natural numbers, the natural numbers that are less than 1. So in simple, if I'm going to write this consists of the natural numbers S is in N such that, all right, S is smaller than 1. And also I could add into this this is bigger than 0, okay, the natural number. Again, we could think there's a bias in here. We know the natural numbers a little bit. All right, now this S is not empty because it does have, by our assumption, it contains A. All right? So let me write this down. It's an important piece of information. All right? I claim that S is not empty since A is in S. The S we have just defined all possible numbers that are smaller than 1. Of course, it's kind of ridiculous. You might think about it by saying, well, it looks like S is going to be empty. Well, we're going to show that it is actually at the end is empty. Okay? But what we're doing logically is all correct. All right? Now, since S is not empty, then by the will ordering principle, because I'm assuming this is to be correct, by the will ordering principle, this implies there exists an X in S such that this is that smallest element, such that X is less than or equal to S for every S in S. Okay, so this is the least element. All right. Now, this X being in S, by the definition of S, implies X in S implies, of course, X is less than 1. I want to multiply this inequality by X. So I'm going to multiply throughout the inequality, this double inequality by X. So we get 0 less than X squared less than X. And I also know that X is less than 1. So this implies that X squared is in S. And we have X squared is smaller than X. Well, that's not true because, but remember that X is let me actually put it in here. That is X is the least element in S. That's really what this statement says. It's nicer to write it in words because that's what we need now. So this implies we have a contradiction in here. So this is contradiction since X squared is smaller than X, and X squared is in S, okay? So this is the least element, so we have a contradiction. Well, if we go back and figure out what did go wrong, so this implies that our assumption, the assumption that there exists an A small in N such that A smaller than 1 is not true. All right? So this is not true, and this implies that actually this S need to be, actually empty. All right, and this exactly means that 1 is less than or equal to n for every n in n. All right. Corollary to this lemma, which doesn't use the will ordering principle in its proof or the principle of math induction. It only uses the lemma, which we already proved, assuming either one of these to be correct. And again, it's another very well-known kind of we use as fact. And it reads like this: there is no natural number between k and k plus 1, between a number and its successor for any natural number k. Again, if someone see you reading, making like this, you think we are wasting your time. We know that. Well, again, this is a statement that we have not. It's not stated in the axioms. We have no theorem to prove this, so this needs a proof. And the proof is very simple. Again, it goes like this. So let's assume that by contradiction again, let's assume that there is a natural number let's see n such that k is less than n is less than k plus 1. So between, it's strictly between them, okay? So we're not putting any equalities in there. We're going to subtract from this, subtract a k. So we get 0, we get n minus k, and we get 1. Now, this statement says this means n minus k is a natural number. All right, it's bigger than, and it is smaller than 1. And n minus k is smaller than 1. Well, this contradicts the lemma. This contradict the lemma. Okay, because we said 1 is the least, is the smallest natural number, and we found the natural number that is smaller than 1. All right, so a good tradition, and again, the only thing which we are incorrect in here is this assumption. That's what it leads to this contradiction. All right, next we're gonna go ahead and prove that. We write this objective. All right. So next objective. To show that the first principle of induction, second principle of induction, and will ordering principle are logically equivalent. Good. This means that if we assume 1, we can prove the other 2, all right, and any one of them. And the way we're going to prove this is first I want to show that the first principle induction and the will ordering principle are equivalent to each other. They are logically equivalent. And then I want to do the second and the will ordering principle. All right? So this is the way we're going to go about the proof of this. Okay? So let me go ahead and start the beginning. So this is the first term. All right, theorem 1 for this part. All right, first principle of induction is equivalent to will ordering principle. Right? So here's the proof. So let's go and actually assume that the will ordering principle actually holds. Okay? And assume that the will ordering principle holds. And I want to show that the first principle of induction actually also holds. So to do this, we're going to define a set of natural numbers that satisfy the condition of the first principle of induction. So we define a set K of natural numbers that satisfy the first principle, the conditions, only the conditions. All right, the first principle of induction. That is, what is this case satisfy? One does belong to K. Two, if K is in K for an arbitrary but fixed K, or sometimes we say for some K bigger than or equal to 1, then K plus 1 is going to be in K. And what we would like to prove at the very end, need to show that the will ordering principle implies, the first principle, this is equivalent to show that this K is equal n. All the natural numbers. All right, to achieve this, we need to define another set. Okay, so we define, basically we need to define another set that we're going to apply the will ordering principle to it. Okay, so we're going to define another set. And this set is basically going to be the complement of this K. But I will define it without referring to the word complement. We're going to define another set T. And this consists of those integers or natural numbers, T in T, such that T is bigger than or equal to 1, and T is not in K. Is not in K. So again, this is basically the complement, okay? So this is the complement of K using set theorem, okay? And the complement is taken, of course, over the natural number, the universe. All right. Now I know that, let me see how I'm going to start with this. We know that actually, since 1 is in K, then 1 is not in T. All right? So I got at least that far. Reorganize my thinking in here just a second. Now let's assume if T is not empty, all right, so let's assume this, then by the will ordering principle, because assuming it's true, will ordering principle, T has a least element or smallest element, and we can call this element, let's say T sub 0. So T sub 0 is in T, and T sub 0 is smaller than or equal T for every T in T by definition of least element. All right. Moreover, we have, based on the definition of T being bigger than or equal to 1, we also have that T sub 0 is bigger than or equal to 1. Since 1 is in in K, okay, but this is by the assumption that K satisfies the conditions of the first principle, then 1 cannot be in T. It's not an element in T. So now, together with these two statements, T bigger than or equal to 1, and 1 is in T, is not in T, and remember that T sub 0 is in T, so these two conditions, be writing next to each other. Now, T bigger than or equal to 1, T sub 0, and 1 is not in T, implies that the T sub 0 is strictly bigger than 1. So it cannot be 1, all right? All right. Now, let's look at the what the corollary is saying. By the corollary, there are no natural numbers between T0 minus 1, because from here we would say that T0 minus 1 is bigger than 0, which makes this a natural number. So this becomes a natural number. Okay, so there is, the corollary says there is no natural number between this, and the next natural number to this is T sub 0. All right, so there is no natural numbers between these, and this would imply that the T sub 0 minus 1 is in fact must be bigger than or equal to actually 1. All right? So this must be equal, bigger than or equal to 1. So we have a natural number bigger than or equal to 1. And then, if I look at T sub 0, remember I can write this one as, again, but let's see, one more thing. And since the T sub 0 minus 1 is bigger than or equal to 1, this implies that the T sub 0 minus 1, all right, is smaller than T sub 0, and T sub 0 is the smallest element, and T sub 0 is the least element. In capital T, and means that the T sub 0 minus 1 cannot be in T. All right, so this implies we're almost at the end, all right? So that implies that T sub 0 minus 1 cannot be in T because this is smaller than the least element. And this means, together with being bigger than or equal to 1, this means T sub 0 minus 1 is in K. All right. Now, we have 1 in K and T sub 0 minus 1 in K by the condition that we impose in K implies their sum. This implies T sub 0 minus 1. So this is like a K, and this is the K plus 1, which is equal T sub 0, and this becomes in K. But we have a contradiction in here. Because T sub 0, it's in T. And the elements in T that are not supposed to be in K. Right? So this contradicts. So these opposing arrows means contradiction. All right? And this means, with this contradiction, since T sub 0 is not in 10. Actually, T sub 0 is in T. It's not in 10. Well, again, if we go back to see what went wrong, is so our assumption that T is not empty led to this contradiction. Well, it means that this is a wrong assumption. So this, therefore, we must have T is empty, and this in term implies K is equal N. Because again, K is the complement, or T is the complement of K, or the K is the complement of T. It's the main difference which way complement is a dual concept. And that's it. So this implies that the first principle of induction holds. First principle of induction holds. All right. All right. Now we're going to continue the going by the other way around. That is, let's assume that the principle of first principle of induction holds, and I want to show that the will ordering principle. Actually, we can prove the will ordering principle is true. All right. So the second part, you're going to assume that the first principle or first induction principle holds. Yes. Induction principle. And we want to do the will ordering. So it means we want to assume let S be a non-empty set of natural numbers. Our objective is to show S has a least or smallest element. Let's assume by contradiction. Assume that S has no least element. Least element. So this means that for every X in S, for every, this one, we know that X is bigger than or equal to 1, all right? Since this is true for, since 1 is the least, is the smallest or least element, in N. And S being a subset or sum of the elements in N, so this is true for every for every X in S. All Now, what does this mean? This means that 1 cannot be in S. So this implies 1 cannot be in S. Because by assumption we say that S has no least element, since 1 is the least element for the whole natural numbers, then it would share, if it exists in S, as a least element. So this must not be the case. All right? Now, again, this implies that we have, for every x in S, we have x is strictly bigger than 1. All right? Now, we need to define another set that actually satisfy the conditions of the induction principle and see what happens from there. All right? So we're going to define this set T. Define T to be the set which consists of all T and T, T and N, such that T bigger than or equal to 1 and T is smaller than S for every S in S. All right? So the elements of T are those natural numbers. They are bigger than or equal to 1. It's any natural number as far as T is smaller than all the elements in S. All right? Now I claim that 1 does belong to T, and this is very straightforward. So first, we have 1 belongs to T, since 1 is bigger than or equal to 1, which means satisfy this condition, and 1, okay, less than S for every S in S. So this is true by our choice of S, non-empty, and it does not have 1 as a least element. So it means every element in S is going to be bigger actually than 1. All right. Now with this, let's assume that let's take an element K in T. All right. And again, this implies that K is bigger than or equal to 1, and K is less than S for every S in S. Now I make the following assumption. If this is a big F, K plus 1 is in S, all right, then so if K plus 1 is let me see it here. So what this means, okay, yeah, then we leave this one in here. We have K is less than S, all right? Let me make sure that I do this one correctly, and this one is less than K plus 1. All right, for some S. and then the S must actually equal to k plus 1. So from here, we conclude that the S, because these are two consecutive natural numbers, and S is a natural number, then if really this is true, means if this k plus 1 is in S, then since there is no natural number by the corollary, there is no natural number, then the S is forced to be equal to k plus 1. All right? So if this one is in S, then it must equal to k plus 1 for some S. Now, and now we have this. Okay, just a little bit here. Okay, so we have here S is going to be equal to k plus 1, all right? And this would imply that the k plus 1 is the least element in S. But this is a contradiction because we assume that S has no least element, all right? So this is a contradiction, which means that the k plus 1 cannot be actually an element in S. So this implies that the k plus 1 is not an element in S. And this means that the k plus 1 is going to be actually in T. But let's see what we have. We have 1 is in T. And if we take k in T, then we proved that k plus 1 is in T. Well, all this together, this implies that T is equal to n. All right, and this proves that actually that the principle of mathematical induction actually follows, because that's what our definition of T actually means. All right. All right. So we have will-ordering principle implies the first principle of induction. All right. Need to now go with the second principle of induction to show its equivalent to will-ordering principle. All right. So I want to state this is as a one other thing actually. I'm sorry. Just looking at my notes in here. So we have shown that T is equal to n, and this implies that actually S must be equal to the empty set. And then we have S has the smallest element. All right. Let me see it. Hence, S must be equal to the smallest element, because the way we defined S, so to go back in here, we defined S to be a non-empty set of natural numbers, and we assume by contradiction that S does not have a smallest element, and we are led to say that with T being equal to n, let me actually clarify this. All right, so this actually implies, yes, it's actually S is empty. So therefore, if S is not empty, then S must have the smallest element. All right, because otherwise we would actually end up with S is empty. So if we assume it does not have one, then that's what it is. All right, now we're going to go to the second principle of induction? All right, so let me write this is as another theorem in here. So theorem 2. The second math or induction principle is equivalent to the will ordering principle. All right. And so let's start with assuming that the will ordering principle actually holds. Okay, so it is approved. So let's assume that the will ordering principle holds. We're going to define a set that actually satisfies the condition again of the second principle of induction. So we're going to let S be a set of natural numbers that satisfy the conditions of the second induction principle, or second principle of induction, I don't know, second principle of induction, I think that's the way we write it. Second principle of induction. Which means that, and these are, one belongs to S, 2, if 1, 2, up to n is in S, then n plus 1 is in S. And we would like to show the n, to show that this S is equal all the natural numbers. Once again, similar to what we've done earlier, we're going to define another set, which is the complement of S. Those elements that do not satisfy these conditions, basically. So we write it down. So we're going to define T to consist of elements x in n, natural number, x bigger than or equal to 1 means, just for emphasis, and x is not in S. All right. Now, again, if we assume T is not empty, but by the will ordering principle, we are assuming it's true. By the will ordering principle implies T has the least element or smallest element. Least element. And let's call this least element x sub 0. Okay, let's say so let x sub 0 in T be the least element in F. Now let's see what this least element satisfies. So this implies that x sub 0 is bigger than or equal to 1, and x sub 0 is not in S. All right? Now, again, since 1 is in S and x sub 0 is not in S, this implies that x sub 0 is supposed to be strictly bigger than 1. All right? So strictly bigger than 1. Now, then for K in S, we take a K in S, then for all natural numbers satisfying this, actually 1 less than or equal to K, less than or equal x sub 0 minus 1, okay, by the second condition, by condition 2, for the elements of S, for elements in S, implies that the next natural number, so this implies that the x sub 0 minus 1 plus 1 is supposed to be in S. So in other words, if you take natural numbers from 1 to x sub 0 minus 1, okay, to be in S, then by that condition implies this, which means it implies x sub 0 is in S, because when you add these, you come up with x sub 0. Well, we're having a contradiction because we know that x sub 0, so this is a contradiction. All right? So this is a contradiction, which means, again, if we go back, this implies the T is actually must equal the empty set. Well, let's see what does this again mean. This means, remember, T is the complement of basically the S, and this means that the S is going to be all the natural numbers, and this proves this proves the second principle of induction. All right. One more thing I need to show is to assume the second principle of math induction and prove actually it implies the first principle. Okay? So next, we show that the second, so that if we assume the second principle of math induction hold, then we show the first principle holds. The first principle of math induction actually holds. First principle of induction. Which is very simple to kind of believe, right? Because the sometimes that we call the second principle actually the strong. So let's do that. So we're going to create a set that satisfies the condition of the first principle of induction, and show this set actually is going to be all the natural numbers. All right. So so we're going to let S be a set of natural numbers such that 1, the number 1 is in S, 2, if K is in S, then K plus 1 is in S. And I want to show, of course, that S is equal to all of N. So our claim is S is equal N. All right. Now remember, we are under the assumption that the second principle of math induction actually holds. All right. Now, from 1, we have 1 is in S. Let's assume that 1, 2, 3, up to K is in S. This in itself, as ridiculous as it might look, that K is in S. Right? Assuming actually all of them, so K is in S. Then by the second principle of induction, this implies K plus 1 is in S. Now, let's look back again. So what we have S is a set of natural numbers. 1 is in S, and if K is in S, then K plus 1 is in S. So in here we have second principle. It says that 1 is in S. Then by the second principle of induction, we have this is K plus 1 is in S. So therefore, we have actually S is going to equal to N. Actually, one more thing. When I say that, okay, so let's assume this by 2 in here. I'm missing this up. Let me remove the whole thing. I'm sorry. Now, it's a very fine line in here, okay? So this implies K and S by 2, actually. By 2 implies K plus 1 is in S. Now we have together, therefore, because we are assuming 1, 2, 3 up to K, and then now we show that K plus 1 is all in this in S, this implies 1, 2, and so on up to K plus 1 is in S, and this implies by second principle of induction that S is equal N. And that's really the claim we need to show it here. All right. So far, we have shown, let me actually write this down in here. Remember, we need to show that the second principle of math induction implies will ordering principle. All I have shown here is this. So we proved that second The first part, we proved that if the will ordering principle holds, then the second principle holds. That's what we've done, okay? So we proved that will ordering principle implies second principle. And I just showed that the second principle implies first principle. Also, we have shown theorem 1, this implication. All right? That the first principle implies the will ordering principle. So this is theorem 1. Now we have a complete cycle. So, which means that this implies that the second principle going through the first principle implies the will ordering principle. So all these together, therefore, we have a complete cycle of implications. Between first principle, second principle, and will ordering principle. All right? So we proved that these together, and there's another thing actually, I need to make this complete. We proved that these also imply each other. All right? So in other words, if I write this one in a more concise way, using abbreviation in here, so if I put in the will ordering principle in here, then I show this one actually goes to first, and then first go to will ordering, going this way, then will ordering go to second, and then second to first, and then we have also will ordering, yeah, we have this one in here. So we have, anyway you start, then always you can go to all others, okay, other implications. All right? We're almost done there. There is still one other form of principle of math induction. It's called third. All right? It's not, really used. I will write it down. I don't know if we will ever need it. But here it is. Okay, so this is the third principle of induction. Again, it says that let K be a set of natural numbers that satisfy or such that one and two is in K. Second is if K plus 1 is in K for some K, then K plus 2 is in K. So if you have a set of natural numbers satisfy these two conditions, then this K is equal to that. All right? All right, I'm going to stop right here. So this actually kind of not, this material, most of it is not actually in the textbook that we are going to be following. So in the next lecture, I'm going to start actually in chapter 1, All right, and in it we can prove some identities or statement using mathematical induction, both the first principle, second principle, the traditional way, basically. All right, as well as the will ordering principle. All right, so we're going to look at actually more of applications of these the principle of induction and will ordering principles, which we will be using throughout, of course, the course. Mathematical induction is very much used in in this course. All right, I'm going to stop right here.